Okay, so today we're going to be talking about parallel computing. And I guess the first question to answer is, what is parallel computing? So parallel computing is when you conduct your computation or your calculations or processes out simultaneously, when you have multiple processes and they happen at the same time. Now, generally what this means, if you've got a large data set or a large problem that you need to work on, is you divide it up into smaller subtasks. And those can be run and solved at the same time. Now, parallel computing is not limited to high performance computing, but certainly it is high performance computing is a platform that makes parallel computing, or one in which parallel computing can really shine. And that's because you have access to multiple processors, multiple CPU cores. So you can take advantage of hundreds, or in some cases thousands of CPU cores to run multiple tasks at the same time. Okay. Now, this is distinct from something called concurrent computing, and we'll talk about what concurrent computing is a little bit more in a second. But
recording which desk you're at, because I can't find where first is. So,
hi, sorry, Jasmine, I think you've got your mic on. Excellent. Okay. So concurrent computing, you may have heard of. This is the sort of computing that you're more likely to encounter on your personal laptop or your PC at home. And we draw the distinction between parallel computing and concurrent computing. Both of those models of computing relate to doing things at the same time, right? So you might have on my laptop in front of me, I have Safari open to look at the workshop materials. I also have Zoom open. I have a bunch of other programs running on my laptop. And what they're doing is, rather than those tasks running simultaneously at the same time, they're actually sharing resources on the core. Okay. But because a computer can think much faster than I can realize, I don't notice that it's swapping between different tasks. Okay. But that's what concurrent computing is. So we'll come back to that in a moment. Now, the importance of parallel computing is that there are some tasks that we will encounter in research that would simply not be possible without parallel computing, because parallel computing allows us to get incredible speed ups to some of the simulations or studies we might be running. And here we've got a quote just saying, for example, if you had a climate change study where you're simulating the climate over thousands of years, these studies can only be done if the time it takes you to simulate like a single year is a few hours, as opposed to multiple days or multiple years. So parallel computing gives us that speed up that is super important to do much of the really intense computational research work that we'll be working with here at Pawsey. So let's talk a little bit more about this. So parallel computing is tied to, I guess, the underlying architecture of the computer that you're using. And I think most of you have heard of Moore's law, okay? And that's basically the prediction that was made several decades ago that the density of semiconductors, or the amount of semiconductors that you could fit onto a single chip, would double over time every 18 months. And that has been largely the case. So from when this law was sort of postulated till now, we've seen a doubling of the capacity of computers' chips to carry superconductors. But there are some limits. One important limit is that as you shrink the size of your semiconductor, controlling the flow of electrical current becomes very hard. Okay, you actually begin to encounter like some very foundational problems with like the physics. You cannot actually make it work down to infinity. Like it just becomes too hard to shrink it even further. And so, as we can see, what that has meant is that we're actually seeing a slowdown in the advancement of semiconductor development. But there's also some problems in power efficiency. So you can make faster chips. You can pack lots of semiconductors on them, but you also get a power efficiency problem. So increasing the speed means that you need more power. And in fact, what you tend to see is that the amount of power that a particular CPU needs is going to increase at a rate that is higher than the speed boost you get out of it. Okay. So how do we overcome this? If the solution is not to make better CPUs, which of course will continue to improve even now, we just use multiple. So we use multiple processors. And by using multiple processors, we can get more computational power out without needing necessarily to have a equal increase in the density of superconductors or even the energy usage. So that's kind of one of the reasons we are using parallel computing. But there are also limitations to parallel computing. And one of those key limitations is that implementing a parallel computing pipeline is not necessarily as straightforward. Okay, so if you want to write code for a serial computing task, it's usually very easy. Like, I hope that all of you have had at least some experience in coding, so you will know if you want to write a program to do a basic task, easy enough to write. But if you want to parallelize that task, that takes time. That involves some amount of complexity, and it also means that whatever complexity you add is harder to debug, right? So the bigger or more complex a program is, the harder it is to find where things go wrong. So even if you do understand what's going on and you know where the problems are and you can debug them, it does involve some time commitment to maintain. So parallel computing can be very, very powerful, but it also comes with certain trade-offs, and that's something to be understood. So if I were to write a script to do one simple task that I'm probably never going to do again, I might just write that script and that's it. I'll just leave the computer going for as long as it needs. But one of the limitations is, sorry, just looking at the chat. That's rarely the case in research. Sometimes our pipelines need to be run multiple times. So rather than having a single script, a serial script running once off that we can just leave for a couple of hours, it might be useful to write a pipeline or an algorithm or a script that is parallelized, that we can run repeatedly and run much, much faster. So that is why we would use parallel computing. Okay. So let us look at the types of parallelism that we have. There are two types depending on what is actually being parallelized. So there's data parallelism and there's task parallelism. Data parallelism means that you have a data set and you have multiple processors that are doing the same thing on different bits of the data set. Okay, so if I have a very, very large file that I need to process in some way, I can have multiple processors maybe looking at different parts of the file. Okay, that's data parallelism. You can also have task parallelism, where you do different things on either the same data or different data, but they're doing different things at the same time. Okay, so data parallelism, the same set of instructions on different parts of a single data set. Task parallelism is you might be doing different tasks. Okay, is that distinction clear to everyone? Any questions about that? Okay, I'm not seeing any questions, so I'm just going to move forward. So now we're going back to talking about concurrency and parallelism. So concurrency, again, is if I wanted to move forward on a particular task, like for example, me personally, I only have one brain, right? So my brain can only do one thing at one time. So for example, I might be delivering this training And then if I were not a very good mentor, I might be looking at my phone every 5 seconds, and then I'd look back at the training. So that would be an idea of concurrency. I would be doing multiple tasks at the same time, right? But I would use my single brain and switch between them, okay? So the examples given here are checking your phone while studying. So you are studying, but you look at your phone, then you look back to your whatever you're studying, or when you're playing a game of chess, so you're taking turns. It also, in a computational sense, what it actually refers to is you have one CPU core that is handling different programs. So as the example I gave earlier is that on my laptop now, I've got the browser open. I've also got Zoom open. So the computer is actually executing instructions for the browser, then executing instructions for Zoom. And it's actually running them in a bit of a chain, okay? It doesn't run them separately at the same time. It runs them on a single core, but bit by bit. So it's dividing those tasks up, and then the first task gets a little bit of time, and then it gives over to the second task. Okay, so that is concurrency. And an important thing about concurrency is that the two things, so like using my browser and using Zoom, don't happen at the same time. Only one can happen at any given time. But because the CPU can actually think very, very fast, right? As it says here, we can multitask on a PC with a single CPU core. So I don't realize that the CPU is actually thinking about Zoom and then thinking about browser and then going back and forth between the two. I don't realize that because the computer is operating on a nanoseconds basis, and my brain operates on a much slower scale. Okay, so that's concurrency. Parallelism is different. Parallelism means that you have tasks that run together at the same time on separate cores. Okay, so the examples given here are you are writing the introduction for your thesis while your numerical simulations are running. So you're doing something while something else is happening. That's basically the concept. Or here as well, if you have two CPUs searching through two halves of a single data set to find a maximum value. So one CPU will take maybe the beginning of the data set, another CPU will take the end of the data set, and they will both conduct the search at the same time. But can we think about reasons that this might create some problems? If you have two processes trying to do the same thing on a data set, just taking this example here, two CPUs searching through two halves of one data set to find a maximum value, what problem might arise from trying to do that? Yeah, so Jasmine's got it. So one happens to move faster than the other, or having to blend after the fact. So that's exactly it. So although parallelism means that things can happen much more quickly, at the end of the day, they actually need to be run in such a way that, you know, we can talk together at the end of the process. Okay, so here, if two CPUs are searching through two halves of one data set to find a maximum value, well, which of those two CPUs has actually found the maximum? Is it the first one or the second one? So the processes need to talk to one another in some way. Okay, so let's look at, before we go further with that concept, let's just look at some helpful terms. First of all, a thread. What is a thread? And you may have heard of CPU cores as being referred to as threads. But in this situation, a thread refers to a subtask. So you have a parallel program, and remember, we divide that parallel program into smaller tasks that can be run at the same time. Those subtasks are threads. Okay. And we have different types of parallelism. We have the shared memory parallelism and the distributed parallelism. And the difference between the two is in shared memory parallelism, you have a parallel process where the threads have access to the same memory. Okay, so that means that if you put your data in RAM, or if you're using a GPU, if you have your data in VRAM, then all those processes read the same memory. Okay, that's shared memory parallelism. It means what it says. In distributed parallelism, it's slightly different. And that's when you have a parallel process where each of those threads, each of those subtasks have their own memory. And what that means is that they don't actually share the same data. They're not looking or reading the same data. Okay. So that's a distinction between shared memory and distributed parallelism. Now, another important concept is synchronization. And that's when the threads will come together to access objects or data that other threads have operated on. Okay, so if you are working on a parallel task, and sometimes those threads actually need to talk to each other, because if they're accessing, for example, the same data, you might need to have those multiple threads report back something to a shared variable. Okay, and that is synchronization. Okay, so the threads will actually access a data or object or a variable that other threads actually also have access to. Okay, so that's synchronization. Now, we're now looking at two issues with parallelization. One is the race condition, and one is parallel slowdown. So a race condition is basically when you have a issue with the parallelism. This is a hard word to say repeatedly. When you have an issue with the underlying parallelism, where if you have the synchronization out of sync, essentially, you might get unexpected behavior, or you might get an error or some fault. Okay. Now, if you have a thread that needs to make a decision based on a shared variable, but you have other threads that are also acting upon that shared variable and they haven't finished, right? Then you're going to get some weird things happening, okay? So you can think about race condition is basically you've got multiple threads racing along, and one of them actually goes a bit further than it needs to because you haven't actually updated the rest of the threads. So you can think of it as like when the threads are racing, but you actually haven't synced them up properly. Okay. You also have a parallel slowdown, and generally we see that parallelization results in your computational processes getting faster, but sometimes that cannot happen. Sometimes it can go the other way. And that is related to, well, setting up the threads to begin with, so initializing them, but also the communication. So the threads need to talk to something, whether they need to talk to memory or whether they need to talk to the disk. There is time spent on that communication. And as you add threads, that communication time increases. So you can actually get a slowdown from parallelization if you haven't optimized it properly. And when we talk about parallelization, we can classify the different tasks into basically three categories. And those are fine-grained, coarse-grained, or embarrassing. Embarrassing is actually what we want. Embarrassing sounds like a bad thing, like, oh, I'm a bit embarrassed about this, but actually in the context of parallelized computing, embarrassing is good. So fine-grained parallelization means that you have threads communicating very frequently. So many times a second, the threads are checking in with each other, okay? Coarse-grained is when the threads communicate infrequently. And embarrassing is when the threads communicate very rarely or not at all. Ideally, you do have embarrassingly parallelized tasks because you decrease the communication time, and therefore you spend more time on computation and not on that communication. So that is almost, in many cases, that's very difficult, if not impossible, to achieve. But embarrassingly parallelized tasks are the fastest category of parallelized tasks. Okay, because they spend less time on that communication. Now, there are a couple ways to achieve parallelization, and there are as we've got here, a couple of languages actually just allow you to write parallel code just like out of the box. So we've got Julia, Corey, Fortran, C#, Java, and they each can handle either shared memory or distributed parallelism. So Julia lets you do both. Corey, Fortran lets you do both. C# and Java let you do shared memory. And there are some parallel APIs and frameworks as well. So these are very common. So we have OpenCL, CUDA, OpenMP, and MPI. So these also work in different ways. So they're all very, very common. OpenMP and MPI are especially common. So you will use the API based on the task that you want to do. And API and good grief, I've already forgotten what the acronym stands for. Something interface. I'll come back to that in a moment. Someone might know the
application programming interface.
That's it. Yeah.
Yeah, it's like a function that you call basically. For example, you have a backend, and in the front end you need to call the things to do the backend. It means you're calling the API.
Thank you.
Yeah.
Appreciate that. This is a great example of parallelization in Fahad's brain because I can only handle one task at a time. And right now I'm handling the training and doing quite poorly at handling the chat. Now, if you're not writing parallel code, then you're going to, but if you're not writing parallel code explicitly, but you want to achieve parallelization, what you're going to be doing is you're probably going to use programs or software libraries that use some of those APIs or frameworks. And so some examples here are NumPy, Intel MKL, TensorFlow. And what of those particular tools you'll use depends on what you're trying to do and also what hardware you have in front of you. So for something like, whether you're working on a GPU task or a CPU task, or what kind of task you have in front of you, do you need to use a shared memory parallelization approach or a distributed parallelization approach? And that kind of speaks to what data set you're working on, what task you're trying to execute. So that is a brief overview of how parallelization operates. So are there any questions before I go forward to chapter 2? Is TensorFlow easier to parallelize than PyTorch? I don't know that I can say for certain. I think it depends. But I also think will we be looking at task parallel frameworks such as SnakeMaker or Nextflow? So it really depends on your particular project, right? So in this training, we're not going to actually look at those particular frameworks. But if you need assistance with one of them, you're always welcome to, just send a message to one of the mentors and we can either walk you through it ourselves or we can find an expert in that field. I know that we do have, and I will get the details to you, but just in terms of resources regarding those particular things, so regarding TensorFlow, PyTorch, Nextflow, we will get, if you would like, we'll get some additional resources out to you about that. And you can talk to the mentors about what it is you're trying to do and achieve, and maybe we can make some recommendations based on that. But we won't be specifically going through those frameworks today. So we're just going to give you an overview, and it may be that some of you will use those frameworks, but some of you may not need to use those frameworks. So it really depends on the kind of project you have in front of you.